Hello, everyone. My name is Aaron Meyer, and I'm a master's student under Dr. Brian McPherson at the University of Utah. Now, I know many of you have recently been wondering, Aaron, how do I remotely characterize a hyperlocal point source of GHG emissions in a dense urban environment using empirical atmospheric data? Well, today's your lucky day, because that's exactly what I'd like to show you in this video.
Alright, I fully realize how dense that title is, so let's break it down a bit. First off, what are GHGs and why do we care? Well, the general scientific consensus today is that human-caused greenhouse gas emissions like carbon dioxide and methane are the leading factor in global climate change. Here we can see that graphically. As CO2 concentration has increased in the past century, so has the global temperature. So we set out to study these gases and how they interact with the environment. The more we know about how GHGs interact with the environment, the better we can evaluate solutions to our climate change problem. This makes accounting for GHGs an interest of policymakers and regulators, and can carry economic implications as more carbon tax and cap-and-trade systems are implemented in the future. Now, while emphasis is often placed on larger global and country scales, accounting efforts are important on all scales, because these smaller scale quantifications are what build national estimates. Here's an example of a city-level accounting program in Los Angeles. So how is GHG flux characterized? Let's take this project from Los Angeles as an example. This project uses a bottom-up inventory approach, which estimates CO2 emissions with proxies like energy use, traffic volume, and land use data at each grid cell to account for GHGs. Another widely studied accounting method uses computational fluid dynamics to create physics-based simulations. These models can range in scale from global atmospheric models like this one from NASA showing atmospheric CO2 concentrations, to smaller scale pollutant dispersion models like this one of downtown Hanover, Germany. Here at the University of Utah, the Environmental Fluid Dynamics Lab works extensively on these types of numerical fluid simulations. Finally, we enter the land of empirical data. This accounting method uses environmental observations, which can take all sorts of forms. Here we'll focus on ground or tower-based atmospheric monitoring, which measures GHGs and other weather data from ground or building-based stations. The University of Utah also has ongoing research in this field through the Atmospheric Science Department, which monitors GHG concentration levels in the Salt Lake Valley using both stationary and mobile stations. This screen cap is from the department's open access website showing this data. Now, just like how global inventories are built on local and state estimates, sensor networks are only as reliable as their building blocks, which in this case are the single atmospheric stations making up the network. If we zoom in to the local level, we can see where many of these stations are placed. Here we can see a station on the roof of WBB at the University of Utah, which collects CO2 and CH4 data along with other weather variables, but we'll focus mostly on the wind. These measurements allow characterization of how air is moving and the GHG constituents present at the monitoring station. Unfortunately, while these single stations are the bones of the broader monitoring networks, they're plagued by uncertainties due to the complex environment. Turbulence is an easy scapegoat for this uncertainty. In general, atmospheric theory tells us that higher up, provided the correct conditions, more stable air movement can be exhibited. As we approach the ground, a boundary layer and still closer this turbulent roughness layer is found. These atmospheric layers show high instability, as chaotic eddies make for unpredictable airflow patterns. Adding to the complexity of this environment are heterogeneous and varied sources of GHGs on the hyperlocal scale. In the case of our environment on campus, these are constituted by roads and parking lots, as well as some larger point sources of GHGs. My advisor Dr. McPherson's keen eye noticed a point source many years ago, in the form of this Panda Express restaurant vent sitting on top of the student union. This vent emits high levels of CO2 and CH4 laden cooking gases. Now naturally, the smell of orange chicken drew me in, And here we are 2 years later with me pulling my head out of this vent. So what happens when one of our sensors is placed in the vicinity of a hyperlocal source like this? Well, suppose the WBB building wasn't available, and our sensor needed to be placed here on the union with the Panda Express vent. When this is the case, multiple studies have shown that these large point sources have a direct impact on the data collected in the form of intense concentration spikes. We can see that illustrated here, as the data collected from the tower near the source shows a daily trend of CO2, but is quite noisy and has these large spikes. So how are they dealt with? Some studies use directional filtering or broad averaging schemes to try to characterize larger trends of GHGs. Other studies find a baseline concentration and examine the trends exhibited in data once this so-called noise has been filtered out. Our study seeks to dive into this noise and these spikes and see if we can extract any useful information from what is often filtered out in larger scale studies. Our hypothesis was that these hyperlocal point sources could be remotely characterized using simple variables like GHG concentration and wind velocity. And we find that this often filtered noise contains valuable information about the source. Now, accomplishing this goal boils down to just 3 easy steps. First, we collect data from the point source and positions around it using different atmospheric monitoring instruments. Next, we create a model from the data. This helps us visualize the relationships between CO2 or methane concentration and wind speed and direction. Don't worry, I'll get more into the statistics. I'm sure that's why you all tuned in for a statistics lecture. Finally, we can interpret the model both visually and quantitatively. We can then use these interpretations to go back and alter different model parameters and look to see what methods and procedures work best for characterizing the source. Alright, well I added a few steps, but let's start with number 1, and that of course is collecting data from the vent itself. In order to effectively check our methods, we need to know how much CO2 is coming out of this just by measuring its outlet point. Doing this was not a trivial task because checking our results directly was difficult. So, to investigate, we built some bench scale models. This allowed us to recreate the vent in a few sizes with a directly measured CO2 input. As CO2 is let out of this canister, the scale records the mass change. This CO2 then flows into the bottom of a vent with an annular shape and is blown upward much like its rooftop counterpart. In this way, we could directly compare our quantification methods with the directly measured mass flow rate reported by the scale. I'm going to skip over the gory details to keep this moving along. I'll happily circle back with more explanation afterward in another video. Our studies found that if the pollutant, CO2 in this case, is well mixed and the velocity exiting the vent is fairly stable in time, we can use continuous point measurements of just concentration and velocity to quantify the mass flow rate from the vent at any given time. The result is the monitoring scheme seen here. By measuring the velocity in blue and the concentration in green, we can estimate the mass flow rate of CO2 leaving the Panda Express vent continuously as seen in red. This tells us that at night the vent is off, or the velocity is 0, and the vent has variable emissions throughout the day. Now, with our vent quantified, we look to collect data remotely in different places on the roof using different types of instruments. The first of these is called an eddy covariance system, which is seen here mounted atop a tower on the roof of the Union. This tower collects CO2, methane, water vapor, and 3D wind velocity data at a very fast rate, 10 data points per second, or 10 hertz. These eddy covariance systems are an industry standard in flux studies, but come at a hefty cost, some costing upwards of $100,000 or more. Now, because of the high cost of these eddy covariance systems, we also set out to investigate how well a low-cost sensor tower would function in its ability to characterize the source. Here we see that in action. with the Panda Express vent seen here in the background. Inside this tower is perhaps what you'd expect the guts of a low-cost graduate student project to look like. It contains 3 spectrometers measuring CO2 concentration in a vertical column on the tower, and a simple cup and vein anemometer as well as thermometer on top of this tower. Data from these instruments can easily be logged to an SD card using a basic Arduino interface. This interface could also be used to broadcast the data to a broader network. Now, once our collection systems were functional, they were deployed to the roof. We collected data concurrently at all 3 stations from August 15th to November 27th of 2019, moving both towers to different locations as seen in the figure. And just like that, it's the end of 2019 and we've collected our data. Time to build a model. We start with some basic data processing. This involved extensive time corrections, filtering out unreasonable values, resampling the data, and calculating wind direction. An important step in the data processing method relates back to this concept of noise and spikes originating from the source itself. Because we are most interested in the elevated levels above the normal daily fluctuations, we examine what I will call an excess concentration. Using a rolling minimum baseline, we can remove these broader daily trends and focus on these excess concentration, those spikes and noise that we think emanate from the source. Once we've completed these pre-processing steps, we enter the world of statistic visualization. Let's start with a basic windrows diagram. This diagram splits wind directions and speeds into bins and plots them in polar coordinates. You can think of this as a type of circular histogram that represents the speed and direction from which wind most often blows. We can then extend this idea to what's called a bivariate polar plot. This operates much like a windrows, where wind directions are binned into delta thetas and wind speeds are binned into delta U or V. Once these bins are established, concentrations can be represented as a function of the wind. Each bin of wind speed and direction holds the associated concentration variables, which allows us to visualize their associated statistics. This plot shows the 95th percentile concentration of excess CO2 at each wind speed and direction. The result is a plot showing hotspots. These hotspots show the wind speed and direction which have the highest associated concentrations. Alright, let's come back up out of the statistics hole. So far, we've collected data and built a model using data processing and statistical visualizations. Let's leave machine learning for now and see what we can find out using these statistical results. We'll first focus on the tower at position 1, about 37 meters east of the vent. Plotting the 95th percentile of raw CO2 values shows us a broad range of potential source directions, both to the northwest and somewhat to the southeast. However, if we create a similar plot using the 95th percentile excess CO2 concentration above the baseline, we isolate the source much more clearly. Here we can see that the direction of elevated concentration points directly toward the known source. This result, and similar plots from other positions, show how useful using the excess concentrations in the statistical methods is for isolating the most influential sources. Now let's move over to the closest position, eddy position 4. Again, the excess plot shows great detection ability, with elevated concentrations coming directly from the source. But we'd also like to extract some quantitative results from these plots. The technique I used was identifying this maximum and its attributes. From this, we can extract the wind speed and direction, as well as the maximum 95th percentile value recorded in the statistical plot. We can therefore see the directional error, or how far off we are, as well as this proxy for estimating source size or distance in this C95 max value, or the maximum 95th percentile concentration recorded in the plot. If we move back to position 1 at 37 meters from the vent, we can see an increase in directional error and a decrease in this C95 max value. This is an expected result, as the farther away we get from the source, the less influential it is on our detection equipment. Moving to the third closest position shows that we're still detecting the source direction fairly well. However, we eventually reach a threshold where the station is too far away or obscured from the source to adequately detect it. Here we see that at position 2, which is about 60 meters away, our 95th percentile technique does not identify the source and instead shows elevated levels coming from the east and southeast. This can be explained by the bus stop here, where multiple buses are often idling, and this is clearly a more influential source due to its proximity. Now, up until now, we focused on the eddy covariance tower, so let's take a look at how the low-cost multi-station does in identifying the source. In fact, we find that the multi-station shows similar performance in directional location ability and these C95 max values. This is an encouraging result, as it shows that the techniques used here apply well to low-cost sensors, and that having a simple anemometer installed with GHG detection equipment could do well to identify nearby sources. So we've been focused on the directional location ability of each position, but we've also been extracting quantitative information from the statistical plots. So now, we can compare the distance from the source with this C95 max value, with the addition of the directional error for each calculation. The exhibited trend looks pretty good. In general, as our distance from the source increases, the presence of these high percentile spikes becomes less influential, and we have lower C95 max values. Additionally, we see the expected result that in general, closer distance corresponds with better directional location ability. We note the outlier here, which is multi-station 2. This station is located on a spot much higher above the roof than the other monitoring stations, and we expect this has something to do with the skew in data here. Okay, so we found that the distance and this C95 max value are correlated. Great. How about the C95 max value and the size of the source? Well, this is actually pretty easy to test because recall that we're concurrently monitoring the vent while collecting data from our towers. Using simple filtering, we can limit the plotted data to when the vent is emitting a certain range of values. Here we can see the bivariate polar plot from position 1 when the vent is completely off, no CO2 is leaving the Panda Express vent. Clearly the most influential source on this plot is coming from the southeast, which is a somewhat expected result given the bus stop there. Now let's see what happens if we turn up the mass from the vent. At low levels of emission, we are still seeing influence from the southeast with low C95 max values. However, as we increase the vent size, we can slowly see that our directional error is reduced, and the larger the source size, the better we are at detecting it. Here is a plot of mass flow rate versus the C95 max value with the included directional error. Here we can see an expected trend. As the amount of CO2 coming out of the vent increases, so does the C95 max value. Additionally, our directional location ability increases significantly the larger the source. Okay, so for the most part we've looked at CO2 as our GHG of choice. This is because we were directly measuring CO2 at the point source. However, we also know that this point source emits CH4 or methane, and does so at much higher levels relative to the ambient background. The result of this larger relative source is that the detectability footprint using our eddy covariance tower is much larger for CH4. We can see that here. Recall that when we were using CO2 as a tracer at position 2, we were detecting mostly this bus lane. But by using CH4 as a tracer, we can effectively locate the direction of the source. Even farther away at eddy covariance station 3, we're still detecting the source, albeit at a much lower C95 max value. When we move to eddy station number 5, we see an interesting result. Although this station is closer than the previous two, we see detection in a completely incorrect direction using CH4. Perhaps there's another source over there. If we take a look at this area on the roof, we can see in fact that, yes, there is another source. While we did not explicitly measure this vent for CH4, we measured it for CO2 at the beginning of the experiment, and the levels were fairly low. However, our results here show that this source is actually more influential at this tower than the Panda Express vent, given some combination of its size and distance. This is pretty cool, as we successfully located a source that we did not know to be emitting CH4 prior to our experiment. This result indicates that using the highest 95th percentile method identifies the most influential source of pollution. In this case, the CH4 coming from the other roof vent, not the Panda Express vent. So we wonder if there is some way to detect the less influential Panda Express vent despite having this more influential vent nearby. To investigate this, let's enter the realm of probability and what are called conditional bivariate probability functions. This very similar plot is calculated by binning all data into wind speeds and directions as we've seen before. Then, the 95th percentile for all concentration values is calculated. The conditional probability is then calculated as the probability that a concentration value will be above the 95th percentile threshold given the condition of its wind speed and direction bin. In this case, there is approximately a 10% probability, given our data, that if the wind speed and direction is in this range, the concentration seen will exceed the 95th percentile threshold seen here. A nice feature of this technique is that we can use ranges of percentile values instead of individual ones. Take this plot for example. This is exactly the same as the previous plot, but instead shows the probability of a concentration falling between the 85th and 95th percentile, a little bit lower than the 95th and above that we've seen before. If we line this up with our tower, we can see that by lowering the percentile to a range of 85th to the 95th percentile, we are actually detecting the source direction. Hooray! Let's test this on a different position to make sure we're not just getting lucky. Recall that plotting excess CO2 for eddy covariance position 2 showed us the most influential source was from the bus stop. Here is the CBPF using a threshold of the 95th percentile, still getting the bus stop. And here is the CBPF using the same range of 85th to 95th percentile. While we're still detecting the bus stop to the east, we can now see that there is an elevated probability of concentrations falling in this range coming from where else but exactly the vent. So this tells us that by varying the statistical thresholds, we can identify different and less influential sources. Clearly we have some pretty cool results out of these statistical methods, but how about we use the buzzword machine learning to try to quantify the source? Well, it turns out that we actually have a really nice system to test this out on. So how would machine learning work in an application like this? Let's take a look. Here we see our CO2 data from the tower, as well as the mass flow rate of CO2 coming from the vent. This is what we want to predict. Let's first scale everything using a min-max scaler to between 0 and 1 for consistency. Now recall we don't simply have CO2 data from the eddy covariance tower, but also the CH4 data seen here, and all of this wind data. Yuck, this looks pretty nasty. So our goal is to be able to predict the amount of CO2 leaving the vent using all of these variables collected at a remote tower. Looks pretty tough using just reasoning or logic, but this is where supervised machine learning really shines. So how do we do this? Well, the first thing we do is split our data into independent sets, one for training the algorithm and one for testing the algorithm. Once we've done that, we can let machine learning do its thing. We use what's called a long short-term memory, or LSTM, neural network to do this. These algorithms work by feeding in all of these variables into a hidden layer of neurons, which then attempt to create an output as close as possible to our measured data. This system is modeled after how we think brains work, with the algorithm learning how input data can be manipulated using relationships and weights to create the most accurate output data possible. This is the training phase. Now, once we've trained this LSTM model, we can test it using our holdout data. To do this, we simply feed the input data into our LSTM model and see what it predicts given how it was trained. Let's zoom in on this testing data. Here in red, we can see the actual empirically collected mass flow rate data. And here in blue is what the machine learning algorithm predicts. Obviously, this looks very noisy, and on small timescales does not look very accurate. However, if we apply a rolling average to both the observational and machine learning predicted data, we can see that in this situation, the algorithm actually does pretty well at detecting the broader trends of CO2 leaving the vent. Pretty cool. Furthermore, if we move to a tower location farther away, like at Ecovariance Station 1, we can see this same noisy prediction from the ML algorithm. The rolling average here shows that there is general trend agreement, but our error is clearly higher due to the distance from the source. Now, there is a lot more work that can be done to fine-tune these models, and additional techniques that can be implemented. But this is a pretty good illustration of the potential of machine learning in this type of application. Whew! So let's take a look back at our original goal. We wanted to be able to characterize a hyperlocal point source using concentration and wind data, and we did just that. We found that using these statistical visualizations and machine learning techniques, we can develop a good idea of the sources which influence each individual station. So what implications does this have, and what future work can be carried out to get us closer to accurate GHG characterization? Our results show that basic statistical techniques can help identify hyperlocal sources, but there is great potential for extending these results and investigating statistical techniques not addressed in this presentation. This is where the statistical model we built is helpful, because we can quickly change many of these parameters and identify the effects that they have on our results. Furthermore, the machine learning techniques presented can be refined extensively. Combining machine learning ensemble methods with our statistical model could help identify parameter spaces allowing for better characterization on various time and spatial scales. Also, additional data would allow an algorithm to continually learn their surroundings, identifying patterns and outliers indicative of environmental GHG interactions. Furthermore, we can extend this work into the CFD realm. Here's a very rough model of the Union Roof using Quick, which is actually helped developed by University of Utah researchers. Using basic inputs, this model shows the general dispersion of CO2 from the source. These forward models could be coupled with machine learning algorithms and statistics to create synthetic datasets. We could therefore imagine a system where an ML algorithm is trained not on empirical data, but modeled data, such that the calibration and training occurs before the sensors are even deployed. What we can then imagine is a network of smart sensors, each characterizing their own local areas using machine learning algorithms, site-specific CFD and synthetic data, and basic statistical inference. Each sensor could then contribute valuable hyperlocal scale information to the sensor networks. This would allow broader networks to characterize GHG flux regionally without losing as much information at the site scale. All three of these fields can help inform one another, and I think the future of emissions detection, quantification, and climate change research as a whole depends on a confluence of all three. I'd like to give a quick shout out to all of those who helped me along the way, with a special thanks to all of those listed here, as well as everybody who helped me lug the tower and seemingly infinite sandbags around the Union roof. I'll leave you all on this summary slide of what we covered today, and hope that you will contact me with any questions that you may have about this research. Thanks for listening.